Welcome to the deep dive. I want you to imagine, just for a second, that everything you think you know about a concussion is, well, that it's wrong.
Or at least wildly incomplete, right?
Right, because usually, when we think of a head injury, we think of a physical bruise on a biological organ. Like, you hit your head, the tissue swells up, you rest in a dark room, and eventually, hopefully, you heal.
Yeah, that's the standard classical view of it.
But what if a traumatic brain injury isn't just a bruise? What if it's actually the violent disruption of a quantum computer?
Oh, it's such a wild concept.
It is. What if a blow to the head is literally scrambling the subatomic processing of the very fabric of your consciousness?
It is a profound paradigm shift. We are just so conditioned to viewing the human brain purely through the lens of classical biology and chemistry.
Yeah, like neurotransmitters crossing synapses.
Yeah, exactly. Electrical action potentials traveling down axons. But the implications of looking deeper, going all the way down past the cellular level into the quantum realm, it completely changes how we understand not just mechanical injury, but human identity itself.
And that is exactly our mission for this deep dive today. We are going to completely deconstruct traumatic brain injuries, TBIs, and chronic traumatic encephalopathy, or CTE.
It's going to be quite the journey.
An epic journey. For you listening, we are going to start with the macroscopic, bone-crushing physics of a car crash. And from there, we'll dive into the microscopic, looking at the immediate chemical tsunamis that destroy brain tissue.
And then into the psychological fallout.
Yes, what actually happens to the mind when the hardware is broken. But we aren't stopping there.
No, absolutely not.
We are plunging straight into the subatomic quantum architecture of the brain itself. We're going to look at the exact structures where consciousness might literally be born.
Right. And finally, climbing back out of that quantum realm to explore the cutting-edge mechanisms the body uses to rebuild the mind.
Like incredibly advanced biological tools, BDNF and stem cell therapies.
It really is a journey from the macroscopic forces of physics down to the unimaginably small quantum world and back up to the psychological reality of the patient.
To do this, we're unpacking a massive stack of incredibly dense, fascinating material today. We've got clinical neuropathology guidelines detailing the exact microscopic geography of brain disease.
We also have advanced theoretical physics and quantum biology theses.
Focusing on something called the Orch-Auer theory, right? And the absolute latest molecular research on neurogenesis, pharmacology, and stem cell treatments. And I have to say, having you here to help connect the dots is amazing.
Well, the most compelling aspect of synthesizing these materials is seeing how completely disparate fields, neuropathology, theoretical physics, molecular biology, they're all unknowingly converging on the exact same microscopic structure inside our neurons.
It's mind-blowing. But before we can talk about the mind or quantum physics or stem cells, we have to talk about the physical reality, the meat, the physical brain inside the skull.
Right, the mechanical event.
Yeah. What actually happens in those violent, terrible milliseconds following a massive impact?
To truly understand the trauma, we have to look closely at the biomechanics of a TBI. And the most fundamental distinction we need to establish right away is the difference between linear forces and rotational forces.
Because the brain isn't just getting pushed in a straight line, is it? The physics of an actual accident are incredibly chaotic.
Precisely. Linear acceleration is what most people picture when they think of a crash. You are moving forward in a vehicle, you hit a stationary wall, your head stops abruptly, and your brain sloshes forward.
Hitting the inside of the anterior skull.
Exactly. That is a linear force, and it is relatively easy for engineers to model in a laboratory setting because the vectors are straightforward. But rotational acceleration, that is where the truly devastating, irreversible damage occurs.
Okay, so what does a rotational force do that a linear force doesn't?
When the head is struck at an angle or whipped around violently, think of, like an uppercut in boxing or a glancing blow in a car spinning out the world. The brain doesn't just slosh backward and forward. It twists upon its own axis.
Okay, let me try an analogy here to visualize this. It sounds like twisting a sealed jar filled with dense gelatin.
Okay, like that.
If I snap my wrist and twist the jar, the glass on the outside moves instantly, right? But the gelatin on the inside lags behind because of its own inertia. It catches up a fraction of a second later.
That is an excellent way to visualize it, but we actually have to add another layer of complexity to your gelatin analogy. The brain is not a uniform consistency.
Oh, right. Because of the different types of matter.
Yes, the brain has different structural densities. You have the gray matter on the outside, which is incredibly dense with the cell bodies of neurons, And then you have the white matter tracts on the inside, which are made up of long, thin, insulated axons.
Like the wiring that connects different regions.
Exactly. And these two distinct tissues have different specific gravities.
So when the head rotates violently, those two different layers are actually moving at slightly different speeds.
Yes. Because they have different densities, they accelerate and decelerate at different rates.
Hmm.
So when the skull rotates, these distinct layers slide and grind against each other.
Oh, wow.
In mechanical engineering, this creates what we call a shearing force. The tissue isn't just being compressed, it's being pulled in opposite parallel directions.
And because the axons are essentially microscopic, fragile biological wires crossing between those layers?
That shearing force literally stretches and tears them apart. This is called diffuse axonal injury, and it is catastrophic.
The structural engineering principles here are just fascinating. When we talk about materials breaking, whether it's steel, concrete, or brain tissue, it comes down to stress, concentration, and strain, doesn't it?
It does. In biomechanics, strain is a mathematical measure of the deformation of a material. Basically, how much can an axon stretch before its structural integrity fundamentally fails and changes shape? Stress concentration, on the other hand, is about the geometric application of that force. If a massive force is evenly distributed across the entire sphere of your skull, your brain can actually handle a surprising amount of energy.
Because it disperses the load.
Exactly. But if that exact same amount of energy is concentrated, say, localized to a specific geometric irregularity inside the skull, or a sudden, sharp change in the brain's tissue density, it creates a mechanical focal point.
The stress multiplies at that specific location.
Right. And when that concentrated stress mathematically exceeds the theoretical cohesive strength of the brain tissue, the cellular structures can no longer hold together. The tissue literally rips on a microscopic level.
I want to pause on that phrase you just used, theoretical cohesive strength, because how do biomechanical engineers actually know what the cohesive strength of human brain tissue is? I mean, we can't just put living people in centrifuges and spin them until their axons snap.
No, ethically, we obviously cannot do that.
Right. But when looking at the history of how these baseline numbers were discovered in the sources, I came across the Wayne state tolerance curve. And honestly, it is a wild, slightly macabre piece of scientific history.
It really is. But it is foundational to everything we know about head safety today. Back in the 1950s and 60s, automotive engineers desperately needed to know how much force the human head could take.
Because they were trying to design the first truly effective car dashboards and modern football helmets, right?
Yes. But as you pointed out, you cannot test lethal force on living volunteers. So Professor Lawrence Patrick and the researchers at Wayne State University took a rather extreme approach.
They used embalmed human cadavers.
They did.
And they didn't just study them on a table. They strapped these cadavers to sleds, or in some experiments, literally dropped cadaver heads down empty elevator shafts onto unyielding steel anvils.
It sounds horrifying by modern ethical standards, I know, but it provided the first real empirical data on cranial impact tolerance. They instrumented these cadaver heads with early accelerometers and pressure sensors.
To measure the actual physics of the crash.
Exactly. They measured the effective linear acceleration, the duration of the impact pulse in milliseconds, and the resulting intracranial pressure of the ICP upon impact.
And by doing this hundreds of times from different heights, angles, and speeds, they plotted out this famous graph.
Yes, the Wayne State tolerance curve. It fundamentally dictates the mathematical threshold where an acceleration acting over a specific tiny duration of time crosses the line from being safely absorbed to being structurally injurious or fatal.
So it's about the time duration as much as the force.
Yes. If an impact pulse is extremely short, say 2 milliseconds, the skull can withstand a massive G-force. But if that same G-force is sustained for 10 milliseconds, it causes catastrophic structural failure.
And this single curve became the baseline for almost all modern head protection safety standards.
It evolved eventually into the GAD severity index used in modern crash test dummies.
It's just wild to think that the 5-star safety rating of my modern SUV is mathematically anchored to cadaver heads being dropped down an elevator shaft in the 1950s.
It's grim, but true.
But it really grounds the conversation in the brutal physical reality of a primary brain injury. Let's use an analogy to separate the timeline of the damage. The primary injury, the literal milliseconds of the initial impact, the bending of the skull bone, the contusions where the brain slaps against the front and back of the cranium, we can call that the earthquake.
That is the perfect framing. The primary injury is an immediate mechanical structural event. The earthquake strikes, and the structural damage is instantaneous.
What kind of damage are we talking about exactly?
In a severe impact, you might see massive hemorrhaging epidural hematomas outside the dura, subdural hematomas beneath it, or interparenchymal bleeding deep inside the brain tissue itself.
And contusions, right?
Yes, which are essentially deep bruises, typically forming at the crests of the brain's folds, the gyri, where the delicate brain tissue grinds directly against the hard, bony ridges of the inner skull.
The earthquake is terrifying. But when you look at the clinical pathology of traumatic brain injuries in the sources, the earthquake isn't actually what kills the patient in the days following the accident.
No, it's not.
And it isn't what causes the devastating long-term cognitive decline. The true danger is the tsunami that comes next, the secondary injury.
Right. The secondary injury is a cascading, microscopic, metabolic catastrophe. Remember the shearing force we discussed?
Mhm.
The tearing of the axons?
Yeah.
When those microscopic biological wires are stretched beyond their cohesive strength, the outer membrane of the brain cell, the axonema, is physically ripped open.
And a healthy axonema is supposed to be a highly regulated, tightly sealed barrier, right? Like it controls exactly what goes in and out of the cell.
It maintains a very delicate electrochemical gradient. But suddenly it's ripped open, the barrier is gone, and an ocean of extracellular ions rushes in, specifically an ocean of calcium. Yes. Under normal circumstances, calcium is highly concentrated outside the neuron and strictly limited inside. But with the membrane torn, massive toxic quantities of calcium flood into the cell, moving down its concentration gradient.
But wait, why is calcium so toxic inside the cell? I mean, we usually think of calcium as a good thing, building strong bones and all that.
Well, in the skeleton, yes. But inside a neuron, excess calcium is a chemical trigger for self-destruction. The massive influx of calcium hyperactivates enzymes called calpains.
Calpains, what do they do?
Think of calpains as microscopic protein shears. Once activated by the calcium, they start indiscriminately cutting up the internal cytoskeleton of the neuron.
Oh, wow.
The cell literally begins to digest its own structural scaffolding.
That is horrifying. And the surrounding cells aren't safe either, are they? Because the damaged neuron starts sending out panic signals.
Exactly. The damaged neuron goes into an uncontrolled state of depolarization. It dumps all of its stored neurotransmitters into the surrounding synapses, specifically massive amounts of glutamate.
And glutamate is the primary excitatory neurotransmitter in the brain, right? It tells other neurons to fire.
Yes, so you have this unregulated, massive glutamate dump, causing a phenomenon we call excitotoxicity.
Meaning the surrounding healthy neurons are being screamed at to fire their action potentials over and over and over again until they literally exhaust themselves.
They fire themselves to death. They deplete their entire microscopic energy reserves, their ATP, trying to keep up with the excitatory signals.
That's devastating.
And at the exact same time, the brain's blood supply cerebral blood flow, or CBF, usually crashes, because the microvasculature has also been damaged in the earthquake.
So let me get this straight. The surrounding neurons are firing frantically, exhausting their energy, but the damaged blood vessels can't deliver the oxygen and glucose they desperately need to produce more ATP to fix their broken membrane.
Exactly. So the brain is simultaneously drowning in toxic calcium, digesting its own internal structure, starving for oxygen, and having a massive electrical seizure at the microscopic level.
And this triggers profound, widespread neuroinflammation and oxidative stress, I'm assuming.
Yes. The production of free radicals skyrockets, further damaging lipid membranes and cellular DNA. And this metabolic tsunami doesn't happen in the milliseconds of the impact. It unfolds over hours, days, and sometimes weeks after the initial mechanical trauma.
So the initial earthquake might tear a few thousand axons, but the resulting biochemical tsunami can destroy millions of surrounding healthy cells.
That's exactly the progression.
Which brings us to the long-term reality. You know, we hear constantly about athletes, military veterans, and people who take repeated, seemingly minor hits to the head over a span of years. This brings us to CTE, chronic traumatic encephalopathy. And chronic is the operative word here, isn't it?
It absolutely is. This isn't a static condition where you get a concussion, your brain is damaged, and you just live with a scar.
Yep.
CTE is a progressive neurodegenerative syndrome. It actively gets worse over time.
It's a disease that essentially feeds on itself long after the impacts have stopped.
Historically, the medical community observed this primarily in older boxers, and we called it punch-drunk syndrome, or formerly dementia pugilistica.
And the symptoms were pretty obvious, right?
Yes, severe tremors, slurred speech, profound memory loss, and aggressive paranoia. But modern pathological scrutiny has revealed that this exact same progressive disease exists in American football players, rugby players, professional wrestlers.
And combat soldiers who've been exposed to the concussive blast waves of improvised explosive devices.
Right.
The ultimate villain in the pathology of CTE is something called the tau protein. Let's really unpack the tau of it all. What exactly is a tau protein? What is its normal job? And why does it go so horribly wrong after a brain injury?
Well, to understand tau, we have to look at the internal architecture of a healthy neuron. Think of a neuron's long axon, like a microscopic railroad track that needs to transport materials, proteins, and mitochondria from the cell body all the way down to the synapse.
Okay, I'm picturing the track.
The structural rails of this track are made of complex polymers called microtubules.
Microtubules. Okay, we are going to be talking extensively about microtubules when we get to the quantum physics part. So for everyone listening, we absolutely need to put a pin in that structure.
Yes, keep them in mind. Now, these microtubule rails are naturally unstable. They actually want to fall apart. So tau proteins are essentially the wooden railroad ties that bind to the microtubules and hold the entire track together. They stabilize the internal structure of the cell.
But when that rotational shearing force hits the earthquake, what happens to the railroad ties?
The violent mechanical stretching physically strains the cell. In response to this trauma and the subsequent calcium tsunami we talked about, chemical changes occur. Enzymes called kinases begin adding excessive phosphate groups to the tau proteins. This is called hyperphosphorylation.
So it changes the chemical shape of the protein?
Exactly. When tau becomes hyperphosphorylated, it physically detaches from the microtubule tract. The railroad ties pop off,
And that causes the microtubule tracks to collapse.
right? Disrupting the cell's ability to transport nutrients, eventually killing the neuron. But the detached tau proteins are actually even more dangerous. They misfold and become highly sticky. They start binding to each other, clumping together into massive, toxic, insoluble aggregates.
And these clumps literally choke the brain tissue.
When these toxic clumps form inside the neurons themselves, pathologists call them neurofibrillary tangles. When they form inside the brain support cells, the astrocytes, they are called astrocytic tangles.
And they just spread, right?
Yeah, these tangles slowly spread from one area of the brain to another, creeping through the neural networks over decades, causing the progressive cognitive and behavioral decline we associate with CTE.
One of the most fascinating details from the clinical neuropathology guidelines is the specific geographic location of these tangles. Like, they don't just appear randomly scattered throughout the brain. There is a distinct pattern.
Pathologists look for a very specific hallmark to diagnose CTE under a microscope. These hyperphosphorylated tau tangles heavily cluster around microscopic blood vessels, specifically at the depths of the sulci.
The sulci being the deep grooves or valleys in the brain's folded surface. Why there?
It goes back to the mechanical engineering principles we discussed earlier, stress concentration. When the brain sloshes and twists, the geometric folds of the brain act as focal points.
Ah, so the biomechanical shearing stress of the initial impact is mathematically magnified at the sharp depths of those valleys.
Precisely. The tissue there is stretched the most violently, so that is where the axillemas tear, the calcium floods in, and the tau proteins first begin to hyperphosphorylate and tangle.
That logical chain from physics to chemistry is just incredible. But I have to push back here, or at least present the tension that exists in the current medical literature in the sources. We see headlines all the time about former athletes suffering tragic mental health crises or unfortunately taking their own lives.
We do, yeah.
And the media immediately, definitively blames CTE and the repetitive hits of their sport. But there is a prominent vein of severe skepticism from highly respected researchers specifically. An author named McCrory is frequently cited in the sources as questioning this definitive narrative. Is the media jumping the gun on assigning direct causality between repetitive subconcussive impacts and the clinical symptoms of CTE? Are we ignoring massive confounding factors?
This is perhaps the most fiercely debated topic in sports neurology today. And we have to be clear, the skepticism from researchers like McCrory is not denying that tau tangles exist.
Right.
It is based on the incredibly strict scientific burden of proof regarding causality in human behavior. We know with absolute certainty that repeated head trauma strongly correlates with CTE pathology, the physical tau tangles discovered post-mortem during an autopsy.
Because you can't definitively diagnose CTE in a living person yet, right? You literally have to slice the brain after death to see the tangles.
Correct. And McCrory argues that definitively proving that historical subconcussive impacts are the sole direct cause of a living patient's complex behavioral symptoms. You know, their depression, their aggression, their suicidal ideation is scientifically incredibly difficult.
Because human life is incredibly messy.
Very messy.
Like if we look at a former professional football player, for instance, they might have a brain riddled with tau tangles, but they also might have lived for 20 years with agonizing chronic joint pain.
Right.
They might have been prescribed heavy opioid painkillers and developed a substance use disorder. They might have suffered a catastrophic loss of identity and social support when they retired from the only life they ever knew. How do you isolate the biological tau tangle from the psychological trauma of their life circumstances?
You have articulated the exact problem. The argument from the skeptics is that the media often conflates the post-mortem discovery of a physical tau tangle with a neat, definitive explanation for the person's entire behavioral decline. This narrative largely ignores the massive compounding effects of clinical depression, the toxicity of substance abuse, or even just normal age-related neurodegeneration.
The concept of cerebral reserve or cognitive reserve plays into this too, doesn't it?
Yes, that is a crucial concept. The human brain has a certain amount of built-in redundancy, a buffer against damage and aging. The literature suggests that repetitive head trauma, even if it doesn't cause full-blown CTE, might severely diminish this cerebral reserve.
Meaning the trauma lowers your defense shields. So if you were genetically predisposed to develop Alzheimer's or clinical depression at age 80, the loss of your reserve means you develop it at age 50.
Precisely. Instead of the trauma being the sole standalone cause of a unique disease, the repetitive impacts might just strip away the brain's compensatory mechanisms, causing the earlier, more severe clinical expression of other underlying psychiatric or age-related neurodegenerative diseases.
That makes a lot of sense.
It is a highly complex, interrelated web. The pathology of the hyperphosphorylated tau is undeniable. But mapping a microscopic tangle of proteins directly to the complex, tragic behavioral choices of a living human being requires us to be exceptionally careful with how we assign causality.
It is a vital reminder that the brain is a complex, chaotic system, not a simple machine. But, to truly understand why this physical shearing, this pulling apart of tau proteins and the collapse of the microtubules has such a profound effect on the mind, we have to look much, much closer.
Yes, we do.
We have to look at what those microtubules might actually be doing. And this brings us to the most mind-bending part of our journey, the quantum brain.
We are now leaving classical Newtonian biology behind entirely and crossing the threshold into the realm of theoretical quantum physics.
I've been waiting for this part. We are diving into the OR theory, orchestrated objective reduction. This theory is the brainchild of what has to be the most incredible, unlikely scientific odd couple in modern history, Sir Roger Penrose and Dr. Stuart Hameroff.
It is a fascinating, unorthodox partnership.
Yeah.
Sir Roger Penrose is a Nobel laureate in physics, an absolute titan of theoretical mathematics, famous for his groundbreaking work on the singularity theorems of black holes and general relativity alongside Stephen Hawking.
Right.
Penrose became deeply interested in the philosophy and physics of the human mind. He wrote a book arguing that human consciousness is fundamentally non-computable.
Meaning it can't be replicated by a classical computer, no matter how powerful it is?
Correct. He believed that the mind's ability to understand mathematical truth and experience subjective awareness cannot arise from classical physics. He proposed that consciousness must arise from the deepest layer of reality we know, quantum mechanics. Specifically, he theorized it comes from the spontaneous collapse of the quantum wave function.
But Penrose, being a theoretical physicist, had a massive biological problem. He had the beautiful, complex mathematical equations for quantum gravity, but he didn't know where in the warm, wet, chaotic, noisy environment of the human brain a delicate quantum process could possibly take place. Usually, quantum states collapse instantly if a single stray photon hits them.
Exactly. To build a technological quantum computer, engineers have to cool the superconducting qubits to near absolute zero in a vacuum to prevent them from interacting with the environment.
A process called decoherence, right?
Yes, but the brain is 98 degrees, filled with rushing water and electrical storms. So Penrose's theory was mathematically sound but biologically implausible. He was stuck. Until Dr. Stuart Hameroff read his book and reached out.
And Hameroff is not a physicist. He is an anesthesiologist.
Yes, his entire medical career is based on the practical application of turning human consciousness off and miraculously turning it back on again, using various anesthetic gases.
Which, as a side note, is still absolutely wild to me that we perform millions of surgeries a year by administering gases that erase consciousness. And fundamentally, the medical field still heavily debates how they actually work on a molecular level.
It's one of the great open questions in medicine. Hameroff had spent decades studying the effects of anesthetics, and his research kept pointing him toward a specific structure inside the neuron, the microtubules.
The exact same structural cylinders we just discussed, the ones held together by the tau proteins.
The very same. Hameroff suggests to Penrose that these microtubules, which form the dense structural cytoskeleton of every neuron, are geometrically and chemically perfectly designed to function as biological quantum computers.
Okay, let's step back for a second and unpack why we would even need a quantum computer in the brain. For almost a century, neuroscience has relied on a very different model. The classic Hodgkin-Huxley model. It's in every textbook. Why is that classic model suddenly not good enough to explain the mind?
The Hodgkin-Huxley model, developed in the 1950s, is the classic integrate and fire model of the neuron. It views the brain cell almost like a simple biological transistor or wire. It proposes that the dendrites of a neuron receive various chemical signals, some excitatory, some inhibitory.
And the cell body simply adds them all up, like an accountant.
Exactly. If the total positive voltage crosses a specific hard mathematical threshold, the neuron's axon fires an electrical spike. If it doesn't cross the threshold, it stays silent. It is very binary, very much like classical computing, ones and zeros.
But there's a massive glaring flaw in this model when you actually look at a living, breathing creature, isn't there?
Yes, there is. The Hodgkin-Huxley model is elegant, and it works beautifully when you isolate a giant squid axon in a petri dish.
Mm.
But when modern researchers implant microelectrodes and look at the axonal firing threshold in individual pyramidal neurons of living, awake mammals like cats engaging in complex behaviors,
Yes.
the firing threshold is completely inconsistent.
We're-
Yes. It varies widely from moment to moment. It is not a fixed, predictable mathematical curve. It is highly dynamic and seemingly context-dependent.
So the Hodgkin-Huxley model is treating a brilliant musician like a simple light switch. A classic computer model simply cannot explain the nuanced, unpredictable behavior of a neuron in a living cat's brain.
Right. So Hameroff looked at this variance and concluded that the neuron isn't just passively integrating signals until a dam bursts. It must be actively regulating and deciding when to fire through some deeper internal computational process.
And that led to OR.
Yes. He and Penrose proposed the alternative orchestrate and fire model.
Yeah.
They suggest that the incredibly dense network of microtubules within the dendrites in the cell body, the soma, are not just scaffolding. They are actively processing quantum information and orchestrated the exact moment the axon should fire.
And the OR theory specifically points to the layer 5 pyramidal neurons. Why are those neurons the prime suspects for consciousness?
Layer 5 pyramidal neurons are the massive primary output neurons of the cerebral cortex. They are structurally enormous, incredibly complex, and possess the densest networks of internal microtubules of any cell in the body.
And they are highly interconnected, right?
Very highly interconnected across the entire brain. If consciousness is a unified phenomenon being orchestrated by biological hardware, these dense interconnected microtubule forests are the prime real estate.
Okay, so let's zoom all the way in on the microtubules themselves, because this is where the biology meets the quantum physics. How on earth does a microscopic hollow biological tube function as a quantum computer?
Let's look at the structure. Microtubules are made of individual peanut-shaped protein units called tubulin. These tubulin dimers snap together to form a lattice, wrapping around into a hollow cylinder. Now, deep within the folds of each individual tubulin protein are hydrophobic pockets.
Hydrophobic meaning water repelling.
Exactly.
Yeah.
These pockets actively push water molecules away. And inside these dry, isolated pockets are specific amino acids that contain aromatic rings, hexagonal carbon structures. These rings share clouds of electrons. In chemistry, we call them pi resonance groups.
Okay.
The electrons in these clouds are delocalized. They aren't tied to one specific atom. They float freely around the ring.
So we have isolated, dry pockets containing clouds of freely floating electrons locked inside the tubulin proteins.
Right. And Hameroff proposes that within these perfectly isolated pockets, London dispersion forces allow for van der Waals dipole oscillations.
Let's break that down for the listener. What is a dipole oscillation?
Imagine the electron cloud shifting slightly to one side of the pocket, creating a negative charge on one end and a positive charge on the other. That's a dipole. It can flip back and forth, oscillate.
Got it.
But because this is happening at the quantum scale, the dipole doesn't just have to be in state A or state B. It can exist in a state of quantum superposition. It can be both A and B simultaneously.
Just like a qubit in a technological quantum computer can be a 1 and a 0 at the same time. This means it can process multiple overlapping possibilities simultaneously.
Exactly.
Yeah.
But as we discussed earlier, the massive problem is decoherence. How does the brain stop thermal noise, the heat and vibration of the human body, from crashing these delicate quantum superpositions before they can compute anything?
This is the genius of the microtubule's architecture, right? The theory suggests that the unique, spiraling, crystalline lattice of the microtubule itself, combined with a highly structured layer of ordered water on its surface, known as the Debye layer, and a surrounding mesh of actin gel, acts essentially as a biological Faraday cage.
That's beautifully summarized.
Yeah.
Yes, it isolates these quantum dipoles from the environmental thermal noise of the brain.
So it creates a localized quantum sanctuary inside the chaos of the cell?
Yes. And because they are shielded, the superpositions don't just stay in one tubulin protein. The quantum states begin to spread and entangle with neighboring tubulins along the length of the microtubule.
And then, through gap junctions, they entangle across multiple neurons.
Exactly. You get millions of tubulin proteins functioning as a single massive quantum state. This large-scale unified entanglement is the orchestration part of ORCH, or R.
So we have an orchestrated quantum computer running inside our neurons, but here is where Penrose brings in his mind-bending theoretical physics. How does a quantum computation actually create a thought? How does a shifting electron cloud create the subjective feeling of being alive, or the color red, or the taste of coffee?
It's the ultimate question.
To answer this, Penrose uses a specific equation for the physics of consciousness, E equals h over t.
This equation is the heart of Penrose's objective reduction. In standard Copenhagen interpretation quantum mechanics, a particle stays in a state of superposition, being in two places at once until it is measured or observed by an outside system.
At which point it randomly collapses into a single state.
Right. But Penrose argues that relying on an observer is paradoxical and doesn't explain how consciousness creates itself. He proposes that the universe has a fundamental built-in physical threshold for quantum collapse, governed by the laws of quantum gravity.
Quantum gravity. We are literally bringing the fundamental fabric of spacetime into the human brain. How does gravity affect a superposition?
Penrose views a particle in superposition not just as a probability wave, but as a physical event. When a mass, like a tubulin protein, is in two states at once, Penrose mathematically argues that it literally splits the fundamental geometry of spacetime at the Planck scale.
Whoa.
It creates a tiny blister, a bifurcation in reality.
So a superposition is reality tearing slightly at the seams.
And that tiny separation of spacetime requires energy to maintain. It has a gravitational self-energy. That is what the E stands for in the equation, E equals h over t. The h is the Dirac constant, a fundamental mathematical constant of quantum mechanics. And t is time.
So E equals h over t means what, functionally, for the brain?
It means that there is a strict limit to how long a split in spacetime can exist. If you have a small mass in superposition, E is small, so t, the time it can remain superposition, can be very long. But in the brain, as millions of tubulin proteins entangle, the gravitational self-energy, E, grows massive.
And then what?
When E reaches a critical threshold, the spacetime blister becomes highly unstable. It cannot sustain itself, and it spontaneously, inevitably collapses on its own. It reduces objectively, hence objective reduction.
And what happens at the exact millisecond of that spontaneous collapse?
Penrose and Hameroff theorized that at the exact geometric moment of that objective reduction, a discrete moment of full, rich, conscious experience occurs.
Wow. So what we perceive as our continuous, unbroken stream of consciousness is actually a rapid-fire series of these quantum bubbles collapsing millions of times a second inside our microtubules.
Yes.
Like the individual frames of a movie reel moving so fast, they create the illusion of smooth motion.
That is the core, staggering premise of the ORCH-OR theory. Our conscious choices, our flashes of insight, our perceptions, are the result of these massive quantum computations halting, collapsing, and selecting specific physical states in the tubulin lattice. Those physical states then mechanically trigger the axon to fire, bridging the gap from the quantum mind to the classical biological brain.
I have to pause here. I love this idea. It is beautiful, it solves the problem of free will, and it sounds like the greatest science fiction concept ever conceived. And I have to play the skeptic here because reading through the literature, the mainstream neurobiological community has not historically been kind to Penrose and Hameroff.
That is an understatement, yes.
I was reading a critique by the philosopher of mind, Patricia Churchlin, and she does not pull her punches. She wrote, and I quote, "Pixie dust in the synapses is about as explanatorily powerful as quantum coherence in the microtubules." That is a brutal takedown.
It is brutal.
She is essentially demanding to know, is there actual empirical laboratory proof for any of this? Or is this just Penrose doing beautiful, elegant math on a blackboard and Hammeroff slapping it onto biology to see if it sticks?
Churchland's critique is highly representative of the establishment view, and frankly, it is a scientifically valid critique. For decades, the Orch-Ora theory was viewed as fascinating, elegant speculation with absolute zero empirical evidence to back it up.
Right.
The explanatory gap between a dipole oscillating in a protein and the actual subjective emotional experience of grief or joy is an absolute chasm. Even if the wave function collapses, how does that physical collapse create the feeling of consciousness? The philosopher David Chalmers calls this the hard problem of consciousness. And Orch-Ora, mathematically beautiful as it is, struggles to definitively bridge that gap.
Right. The theory might tell us where the switch flips and the math of how the switch flips, but it doesn't explain why the light has a specific color or feeling when it turns on.
Exactly. However, we have to acknowledge that the landscape of quantum biology is shifting rapidly. Recent, incredibly sophisticated experimental data is starting to chip away at that skepticism. We are finding that biology uses quantum mechanics much more than we thought in photosynthesis in avian navigation. And regarding microtubules specifically, the text highlights new computational simulations analyzing the tryptophan networks within them.
Tryptophan, that's an amino acid, right? The one famously and mostly incorrectly blamed for making us sleepy after eating turkey.
Yes, tryptophan is an amino acid, and crucially, it contains an indole ring, a complex aromatic structure rich in those delocalized pi electrons we discussed earlier.
Oh, okay.
Microtubules have dense, ordered networks of these tryptophan molecules. Researchers ran massive supercomputer simulations predicting how these networks would handle energy. And the simulations predicted that under specific conditions, microtubules could exhibit a phenomenon called UV superradiance.
UV superradiance. The name makes me think of a synchronized laser beam rather than a bunch of individual flashlights. Are these microtubules somehow sharing photons to lock themselves into a unified quantum state?
Your laser analogy is remarkably accurate. Superradiance is a profound quantum mechanical effect. Normally, if you excite a group of atoms with light, they will absorb the energy and randomly, independently emit photons back out over time.
Like flashlights.
But in superradiance, the atoms enter a synchronized quantum coherent state. They act as a single, unified quantum system. As a result, they emit a massive, intense, instantaneous burst of light much faster and brighter than they possibly could individually. It is absolute proof of quantum cooperation.
Like an entire stadium of people doing the wave perfectly synchronized instead of just randomly standing up and sitting down. So the computer simulated this. Did they actually prove it in a lab?
They did. Researchers took real lab-grown networks of microtubules and blasted them with ultraviolet light photoexcitation. They then measured the quantum yield, which is the exact ratio of photons emitted compared to photons absorbed.
And the results?
They found that the observed quantum yield of the microtubule networks was significantly, massively higher than the yield of individual separated tubulin proteins. The data perfectly aligned with the predictions of the superradiance simulation.
So it actually works.
This implies, with empirical data, that microtubules are physically capable of sustaining large-scale, cooperative quantum states.
So while it might not definitively solve the hard problem and prove how consciousness feels, it absolutely proves that the biological hardware is capable of running the quantum software without melting down at body temperature.
Correct. It proves that the biological substrate can support the exact physics required by the Orch-Ora theory. The microtubules are not just dumb structural pipes, they are highly advanced quantum conductors.
This bridges us perfectly back to the reality of the patient. If consciousness is this unbelievably delicate, beautifully orchestrated quantum computation happening inside the microtubules, and if a traumatic brain injury, that rotational shearing force physically rips apart those exact same microtubules by stripping away the tau proteins, what happens to the person?
It's devastating.
What happens to the mind when the quantum hardware is violently scrambled?
This is where the theoretical physics translates into immense human tragedy. We're looking at the psychological fallout of a torn neural web. And to ground this abstract concept in clinical reality, we have to look closely at the frontal lobe of the brain.
The frontal lobe is the real victim in most severe TBIs, isn't it? Because of the anatomy of the skull we discussed earlier.
Yes. The inside of the human skull is not a perfectly smooth protective bowl. The frontal bone, right above the eye sockets, the orbital roof, and the cribriform plate and the sphenoid ridges in the temporal areas are jagged and bony. They have sharp crests.
So when the brain sloshes around...
When the brain sloshes and twists from a severe impact, The soft underside of the frontal lobes takes the absolute brunt of the grinding, shearing force against those bony ridges.
It's like dropping a wet sponge inside a ceramic bowl lined with coarse sandpaper and shaking it violently.
That is exactly what happens mechanically. And the tragedy is that the frontal lobe is the evolutionary seat of our highest level cognitive functions. It is the absolute command center for personality, impulse control, working memory, and emotional regulation. It is the part of the brain that makes us uniquely human.
So when that specific area is sheared apart and the microtubules collapse, the person fundamentally changes. The clinical sources detail specific behavioral symptoms that arise, and they are just heartbreaking for families to witness. Let's look closely at one crucial distinction the literature makes: adynamia versus depression.
This is a vital, frequently misunderstood clinical distinction. To family members and even to inexperienced clinicians, they could look identical from the outside. The TBI survivor sits on the couch all day, sleeps late, doesn't engage in personal hygiene, ignores their hobbies, and shows absolutely zero interest in social activities. The family naturally assumes the survivor is profoundly depressed.
Which is a completely logical assumption, because who wouldn't be deeply depressed after suffering a life-altering brain injury and losing their previous capabilities?
Exactly. Reactive depression is very common. But adynamia is a fundamentally different pathological mechanism. It isn't just laziness, and it isn't an underlying emotional sadness. Adynamia is a profound neurological inability to execute the cognitive processes necessary to initiate an action.
So it's not that the emotional gas tank is empty, it's that the physical starter motor is broken.
That is the perfect analogy. The neural pathways connecting the anterior cingulate cortex, which drives motivation, to the supplementary motor areas, have been sheared apart.
Oh, wow.
The patient might sit on the couch and internally think, I should get up and make a sandwich. I'm hungry.
Yeah.
The intention is there. But the neurological bridge that translates that intention into the physical action of standing up is gone. They aren't choosing not to act. They are trapped behind a broken transmission.
Wow. To be locked inside your own head like that. And then there's a condition called alexithymia. That word literally translates from Greek as no words for emotions.
Alexithymia is perhaps the most devastating symptom for interpersonal relationships. It is the profound loss of empathy. But we have to understand that this loss of empathy is entirely mechanical, not malicious.
How so?
Empathy requires complex neural networks like the mirror neuron system and connections to the insula to simulate another person's emotional state within your own brain. When those networks are sheared by rotational forces, the survivor loses the biological ability to identify, describe, or physically feel what another person is feeling.
So if a spouse is crying in front of them, they don't feel a sympathetic pang of sadness. They just see water leaking from eyes.
Yes. They may appear incredibly egocentric, cold, or completely uninterested in their loved one's pain, but they simply cannot process the data. Furthermore, they lose the ability to process their own internal emotions.
That sounds terrifying.
They might feel a racing heart and sweaty palms, but without the frontal lobe to interpret those signals, they don't know if they are angry, terrified, or excited. This leads to massive internal confusion and frustration.
And that frustration can leak out explosively, which leads us to disinhibition and emotional lability.
Yes, disinhibition is the literal loss of the frontal lobe's brakes. The orbitofrontal cortex normally suppresses the primal emotional urges of the amygdala. When those top-down inhibitory pathways are torn, the survivor loses all impulse control.
So they act out.
They might say highly inappropriate or offensive things, engage in dangerous, risky behavior, or completely miss subtle social cues because the filter has been physically removed.
And an emotional ability.
Lability is characterized by intense, rapid, and wildly fluctuating emotional responses that are totally incongruent with the actual situation.
This makes me want to expand on the analogy we started building earlier. If we tie this clinical psychology back to the Orch or quantum theory, the healthy brain is a world-class symphony orchestra. All the musicians, the neurons are entangled. They are all looking at the exact same sheet music, playing a beautifully synchronized symphony.
Yes, the orchestration.
But the violent rotational shearing force of the TBI literally tears the sheet music to shreds and fires the conductor. The instruments, the primal emotions of the amygdala are still there, and they are still playing. But without the quantum orchestration of the frontal lobe to synchronize them, they are playing wildly out of context.
Exactly.
You get a brain where the violins are playing a funeral march while the brass section plays a circus theme. You get a patient laughing hysterically at a funeral or experiencing intense, unprovoked paranoia that their spouse is trying to poison them.
And then there's the phenomenon of perseveration, where the orchestra gets stuck on a single repetitive loop of music and mechanically cannot stop playing it.
Like a broken record.
Yes. The survivor's brain locks onto one task, one topic of conversation, or one anxious thought pattern, and they literally cannot break the neural loop even if they are consciously aware they are repeating themselves. The cognitive flexibility required to shift gears is gone.
So, if the quantum hardware is damaged and the symphony is out of tune, how do you even begin to cope with this clinically? It's not like you can put the brain in a cast.
Management is incredibly grueling and requires a multidisciplinary approach. The clinical guidelines specifically highlight the efficacy of cognitive behavioral therapy, or CBT.
How does CBT help with physical damage?
CBT is vital because it acts as an external manual override for the damaged frontal lobe. A neuropsychologist works relentlessly with the survivor to help them intellectually recognize their problematic thoughts, triggers, and emotional loops.
So if the automatic emotional regulator, the brain's thermostat, is broken, you have to teach the patient how to manually adjust the temperature using pure conscious logic.
Precisely. It is utilizing neuroplasticity through behavioral repetition. They teach specific anger and stress management techniques to deal with the lability. They use mindfulness training to try and anchor the survivor's attention in the present moment, which can help short-circuit the loops of confabulation and paranoia.
It must be exhausting work.
It is exhausting. Essentially trying to build a new bridge of neurons around the massive chasm left by the injury.
And that concept of building a new bridge pivots us into the final and most hopeful part of our deep dive. We've talked extensively about the physical damage, the quantum scrambling, and the psychological devastation. But the human brain is not entirely defenseless. Let's talk about the body's counterattack. How, on a microscopic level, do we actually rebuild the hardware?
The foundational concept of this entire rebuilding process is neuroplasticity. The brain's innate ability to physically reorganize itself, sprout new dendrites, and form entirely new neural connections. But the sources we are analyzing are very careful to point out that neuroplasticity is not always a benevolent force.
It's a double-edged sword.
It is. We have to distinguish between adaptive plasticity and maladaptive plasticity.
Right, because sometimes the brain's panicked attempt to fix itself actually creates permanent roadblocks. And the ultimate example of that is the glial scar.
The glial scar perfectly encapsulates this dual paradoxical nature of the brain's healing process. Immediately after the injury, the brain mounts an acute neuroinflammatory response. Microglia and astrocytes, the support cells of the immune system, rush to the site of the lesion.
And in the very acute early phase, this response is entirely beneficial, right?
Yes. They act like a microscopic hazmat team, phagocytizing and clearing away the cellular debris, the dead tissue, and the toxic spilled proteins.
Right. But the problem is, once the hazmat team finishes cleaning up, they don't pack up and leave.
They don't. These astrocytes undergo a process called hypertrophy. They swell up, change their genetic expression, and become reactive. These reactive astrocytes densely intertwine to form a massive structural and chemical barrier entirely surrounding the injury site. This is the glial scar. Now, initially, this scar is a lifesaver. It physically walls off the damage, preventing that toxic metabolic tsunami of calcium, calpains, and free radicals from spreading into adjacent healthy brain tissue. It isolates the fire.
It's a fire break. But the long-term downside is that once the fire is finally out, you are left with a giant, impenetrable biological wall right in the middle of your neural circuitry.
Exactly. The glial scar becomes a severe impediment to long-term recovery. When the surviving neurons eventually try to grow new axons to reach across the void and reconnect the broken circuits, their microscopic growth cones hit this dense scar tissue and are physically blocked.
They just hit a wall.
Worse, the scar actively secretes inhibitory molecules, specifically chondroitin sulfate proteoglycans, that chemically repel axonal regeneration. The axons simply give up and retract.
So the clinical goal of regenerative medicine isn't to blast the glial scar into oblivion because you desperately need its protective benefits in the beginning. The goal is to modulate it, to soften the mortar of the wall just enough so new, healthy wires can punch through.
Precisely. And the absolute master architect of that delicate rebuilding process is a molecule called BDNF, brain-derived neurotrophic factor. In the literature of neuroregeneration, BDNF is treated almost as the holy grail.
Let's look really closely at BDNF because its mechanism is fascinating. It's a neurotrophin, meaning it's a protein specifically designed to regulate the survival, development, and function of neurons. And the research details a very specific biphasic release of BDNF after a traumatic injury. How exactly does that two-part wave work?
Biphasic means the brain deploys BDNF in two distinct temporal waves, with two entirely different goals. Within 30 minutes to 4 hours post-injury, there is an immediate, massive, localized surge in BDNF production. This is the brain's emergency triage response.
And what does it do in that triage phase?
In this acute phase, BDNF acts to aggressively suppress apoptosis, the programmed cell death that the calcium tsunami is trying to trigger. It binds to receptors and activates intracellular pathways like DCL2 to keep the severely damaged, teetering neurons alive through the metabolic storm.
It's essentially performing microscopic CPR. That's phase 1. What about phase 2, the long-term phase?
Phase 2 is sustained over several weeks or even months during the recovery period. BDNF levels remain chronically elevated in the surrounding tissue to promote two critical functions: neurogenesis, the actual birth of brand new neurons from neural stem cells located in the hippocampus, and the massive driving of dendritic growth in existing neurons.
Let's zoom in on how it drives that dendritic growth because the mechanics of it are incredible. The BDNF doesn't just wash over the cell, it has to unlock a specific door. It binds to something called the TRKB receptor, right?
Yes. BDNF is the highly specific chemical key, and the TRKB tropomyosin receptor kinase B receptor is the complex lock embedded on the outer membrane of the neuron. When BDNF successfully binds to TRKB, the receptor dimerizes two parts of it, snap together, and it autophosphorylates.
And what does that do?
This activates a massive, cascading intracellular signal transduction pathway deep inside the neuron. And one of those vital end results of this pathway is the modulation of a structural protein called actin.
Actin. We mentioned actin earlier when talking about the protective gel around the quantum microtubules. It's a foundational scaffolding protein.
Exactly. By activating complex pathways like PI3K and ACT, BDNF literally causes actin filaments to rapidly polymerize. It forces the internal scaffolding of the neuron to push outward, physically changing the shape and expanding the size of dendritic spines.
Which are the tiny mushroom-like protrusions on dendrites where synapses actually form.
Yes.
So BDNF is literally forcing the cell to reach out and build larger docking stations for incoming signals.
Yes. By making these dendritic spines physically larger, more complex, and packed with more receptors, BDNF massively enhances synaptic transmission. It permanently strengthens the electrochemical connections between neurons.
That's amazing.
This structural strengthening is the fundamental biological mechanism of long-term potentiation, or LTP. And LTP is the physical basis of all learning, memory, and cognitive recovery.
So BDNF is literally the construction form in rebuilding the quantum hardware. The dendritic spines and the microtubule networks trying to get the symphony orchestra playing together again. But if BDNF is the foreman, how do we hire more of them? The text highlights that modern pharmacology is intensely focused on molecules that can boost BDNF levels.
It is a massive area of research, and the sources highlight several highly promising compounds, ranging from natural dietary supplements to advanced synthetic drugs. On the natural side, we see extensive data on curcumin, the active compound found in turmeric, and transresveratrol, found in the skin of grapes.
Right.
Both have been shown in animal models to significantly elevate BDNF levels in the hippocampus and cortex following an injury.
Although with curcumin, the classic problem is always bioavailability, right? It's notoriously difficult to get it to cross the blood-brain barrier unless it's packaged in a liposome or paired with something like piperine.
That is the constant hurdle in neuropharmacology. You can have a miracle molecule, but if it can't cross the blood-brain barrier, it is practically useless. This is why researchers are developing synthetic compounds designed specifically to cross that barrier and target these pathways.
Like J147.
Exactly. The text prominently mentions J147, a synthetic compound originally developed for Alzheimer's research that targets mitochondrial ATP synthase, which surprisingly triggers a massive increase in BDNF and shows incredible promise in neuroregeneration.
And then there's a molecule called 7,8-dihydroxyflavone. When I was reading about this, my mind was blown. It's not just boosting BDNF production, it's bypassing it entirely.
7,8-DHF is a fascinating synthetic prototype drug. It is a flavone that was discovered during high-throughput screening of thousands of chemicals. It is designed to be a direct TRKB agonist.
Meaning it structurally mimics the BDNF key perfectly.
Yes. Unlike the actual BDNF protein, which is large, fragile, quickly degraded by enzymes in the blood, and cannot easily cross the blood-brain barrier, 7-or 8-DHF is a small molecule. It can be taken systemically, slip past the barrier, float right up to the neuron, and insert itself directly into the T or KB lock.
Triggering that exact same actin polymerizing, spine-growing regenerative pathway without needing actual BDNF to be present.
That is incredible engineering.
But BDNF isn't the only critical growth factor in the brain's arsenal. The sources also heavily discuss NGF, nerve growth factor, and how modern researchers are using literal nanotechnology to deliver it into the hostile environment of the injury site.
NGF is crucial for the survival and growth of sympathetic and sensory neurons. But in a severe acute TBI, the endogenous NGF, the natural supply produced by the surrounding tissue, is rapidly depleted and degraded by the massive inflammatory storm. The microenvironment becomes incredibly toxic, and this creates a devastating cascading failure.
Because without NGF acting as a beacon, the body's stem cells get confused.
Exactly. When endogenous neural stem cells migrate to the injury site, they sample the chemical environment to decide what kind of cell they should mature into. Without sufficient NGF signaling them to become neurons, and surrounded by the inflammatory cytokines of the glial scar, the stem cells default to the easiest path.
Which is?
They differentiate into more astrocytes. They just add more bricks to the scar tissue wall, instead of becoming the intricate wiring the brain actually needs to heal.
So they become bricklayers instead of highly trained electricians. To fix this, researchers have engineered what the text calls neurophilic biomimetic lipoproteins. Let's break down that jargon, because the reality of what they're doing is like building a microscopic Trojan horse.
That is an excellent analogy. A biomimetic lipoprotein is a highly engineered synthetic lipid vesicle. It is a microscopic bubble made of a phospholipid bilayer, specifically designed to perfectly mimic the biological structure of the body's own natural cell membranes. Researchers pack the inside of this fat bubble with a concentrated payload of exogenous lab-grown NGF.
And because the outside of the bubble looks exactly like natural biology, the body's immune system ignores it, and it can slip right past the blood-brain barrier.
It acts as a stealth delivery system. It navigates directly to the lesion site and releases the concentrated NGF directly into the hostile microenvironment.
Tricking the stem cell.
Yes. By artificially flooding the zone with NGF, it chemically tricks those migrating neural stem cells. It forces them to differentiate into mature, functioning neurons, actively rebuilding the complex circuitry instead of just blindly building more scar tissue.
Which brings us to the ultimate heavy artillery of modern regenerative medicine, stem cell therapy itself. The sources draw a very strict line between endogenous stem cells and exogenous stem cells.
We just discussed endogenous neurogenesis, attempting to stimulate and direct the brain's own naturally existing but highly limited supply of neural stem cells residing in the subventricular zone.
But there's a problem with that.
The clinical problem is that in an adult human, this endogenous reservoir is extremely small, and coaxing those few cells to physically migrate across the brain to a toxic injury site, survive, and successfully integrate into complex existing neural networks is incredibly difficult. They are simply overwhelmed.
So if the local militia is overwhelmed, we have to bring in massive outside reinforcements, exogenous stem cells. The sources focus heavily on a specific type, mesenchymal stem cells, or MSCs. Where do we actually get these cells for therapy?
MSCs are multipotent stromal cells that can be harvested from several places in the adult body. Bone marrow is a common source, as is adipose tissue or fat. But currently, the most clinically promising source for neurological trauma is human umbilical cord tissue.
Really?
Yes, umbilical cord-derived MSCs are incredibly robust, highly proliferative, and show tremendous therapeutic promise in severe TBI models.
Now, I have to admit a fundamental misunderstanding I had before reading this material. I always thought that in stem cell therapy, doctors inject millions of stem cells into the brain, and those blank cells simply turn into brand new neurons to replace the dead ones on a one-to-one basis. But the text explicitly states that's not how it works at all.
That is the most common public misconception regarding stem cell therapy. While it is true that MSCs can be forced to differentiate into neural phenotypes in a highly controlled petri dish environment, when they're actually injected into the chaotic, toxic environment of the living TBI patient, their primary mechanism of action is not cellular replacement.
So they don't become neurons.
Very few of them actually become neurons. Instead, they act as microscopic, highly advanced chemical factories.
They are essentially a massive pharmaceutical manufacturing plant injected into the tissue. What are they manufacturing?
The clinical term is the paracrine effect. The injected MSCs secrete an unbelievably complex secretome consisting of hundreds of different growth factors, cytokines, and extracellular matrix substances.
And how do they deliver that?
They release these payloads packaged inside exosomes, tiny, lipid-bound vesicles that travel to adjacent damaged cells. Through this secretome, the stem cells essentially act as the ultimate diplomats and peacekeepers in the war zone of the injured brain.
Give me a specific example of how these stem cell exosomes act as peacekeepers. The sources detail their interaction with something called the NFKB pathway.
NFKB nuclear factor kappa B is a critical protein complex. It acts as the absolute master genetic switch for the cellular inflammatory response. When the brain is injured, NFKB enters the nucleus of the cell and triggers the massive production of pro-inflammatory cytokines, fueling the destructive secondary tsunami.
It turns the inflammation dial up to 10.
Exactly. But the exosomes secreted by the umbilical cord MSCs contain specific microRNAs that enter the damaged brain cells. These microRNAs directly inhibit the degradation of a protein that holds NFKB hostage in the cytoplasm.
Oh, wow.
By locking NFKB out of the nucleus, the stem cell exosomes literally reach in and flip the master inflammation switch to off. They drastically immediately reduce the secondary inflammatory damage and halt widespread neuronal apoptosis.
But they don't just stop inflammation at the cellular level. The most staggering thing I read was how these stem cells literally reprogram the body's immune system. The text describes how MSCs trigger the transdifferentiation of T helper 17 cells into T regulatory cells. Walk me through that, because that sounds like biological alchemy.
It is one of the most elegant mechanisms in all of biology. T cells are the foot soldiers of your immune system. T helper 17 Th17 cells are highly aggressive pro-inflammatory immune cells. In a brain injury, they swarm the area, secreting interleukin-17, attacking tissue, and making the neuroinflammation much worse.
Okay, so they are the attackers.
On the other hand, T regulatory Treg cells are the immune system's peacekeepers. Their job is to suppress the immune response, secrete anti-inflammatory interleukin-10, and promote healing.
So you have aggressive soldiers and peaceful medic?
When the MSCs are injected, they assess the chaotic environment and release specific signaling molecules like TGF-beta and indoleamine 2-choline-3-dioxygenase IDO. These chemicals physically bind to the aggressive Th17 cells. And they don't just kill them, they alter their genetic expression.
They force the aggressive Th17 cells to completely change their cellular phenotype and transform into peaceful Treg cells.
Yes.
They literally convince the attacking army to drop their weapons and become combat medics.
They totally reprogram the immune landscape. By halting the cytokine storm and converting the immune cells, the stem cells create a calm, nurturing, anti-inflammatory microenvironment where the brain's own limited endogenous repair mechanisms driven by the BDNF we discussed earlier can finally get to work rebuilding the shattered microtubule networks.
Okay, looking at all of this together, if the brain has this unbelievably advanced regenerative toolkit, BDNF rebuilding dendritic spines, biomimetic nanoparticles delivering NGF, and umbilical stem cells literally reprogramming aggressive immune cells, why are we still failing to fully cure severe TBIs? Why is a severe brain injury still a permanent, lifelong disability for millions of people?
Because the clinical and logistical hurdles are still immense. First, managing the profoundly hostile microenvironment of the secondary injury is a frantic race against time. If the calpain enzymes shred the cytoskeleton before the BDNF can stabilize it, the cell dies, and no amount of stem cells can bring a dead neuron back.
Right.
Second, as we discussed, safely overcoming the physical barrier of the mature glial scar without causing further surgical hemorrhage is incredibly delicate.
Yeah.
Third, the actual route of administration for stem cells is still highly controversial and being optimized.
Do you inject them directly into the brain lesion, which causes further mechanical trauma?
Exactly. Or do you inject them intravenously, hoping enough of them survive the journey and successfully cross the blood-brain barrier to be effective?
And finally, there's the one variable none of us can escape: age.
Age is the ultimate, unavoidable confounding factor in neurorecovery. Neuroplasticity, endogenous stem cell reservoirs, and baseline BDNF expression drop precipitously as the human brain ages.
Which makes sense.
The robust, aggressive, regenerative response we see in a young developing brain is severely blunted or entirely absent in an older adult. This is exactly why a mild concussion in a 20-year-old collegiate athlete resolves very differently, both mechanically and psychologically, than the exact same biomechanical impact in an 80-year-old individual. The biological scaffolding simply cannot repair itself at the same speed.
Wow. We have covered an absolutely unbelievable amount of ground today. We've traveled from the macro to the micro and back again. Let's pull all these disparate threads together for you, our listener, to see the whole tapestry.
It is a vast, deeply interconnected landscape of human vulnerability and biological resilience.
We started with the brutal macroscopic physics of the impact the linear and rotational shearing forces, mapped out by cadavers falling down elevator shafts, that literally tear apart the brain's white matter tracks.
And we watched as that mechanical earthquake unleashed a metabolic tsunami of calcium and glutamate.
Forcing neurons to digest their own scaffolding, we saw how those tearing forces ripped the tau railroad ties off the microtubules, leading to the toxic tangles and progressive, creeping devastation of CTE.
From there, we plunged past the biology into the bizarre quantum realm with the Orch-R theory. We explored the possibility that those very same microtubules might not just be structural pipes, but the ultimate quantum computers of the mind.
We looked at how they might orchestrate van der Waals dipole oscillations, shielding them from thermal noise, to produce the actual subjective experience of consciousness through Penrose's objective reduction of space-time gravity.
And we saw the heartbreaking psychological tragedy that unfolds when that delicate quantum hardware has damaged the adenamia that traps a person in their own body.
The alexithymia that destroys empathy, and the disinhibited symphony orchestra playing wildly out of tune due to frontal lobe damage. But we refused to end in despair. We looked at the microscopic builders BDNF polymerizing actin to reshape dendritic spines, biomimetic lipoproteins smuggling NGF past the immune system, and umbilical stem cells acting as master chemical factories to reprogram aggressive T cells and rebuild the torn web.
It highlights the profound fragility of the human mind, while simultaneously revealing the staggering, almost unimaginable complexity of the biological tools trying to save it. And I want to leave you with a final lingering thought.
Please do.
Think about the entire scope of everything we've discussed today. If Sir Roger Penrose and Dr. Stuart Hameroff are actually right, if human consciousness isn't just a passive byproduct of classical chemical reactions, but is actually the fundamental spontaneous collapse of quantum states inside the dry hydrophobic pockets of our microtubules, then what does medical recovery actually mean?
That's a profound question.
When we use advanced stem cell exosomes and synthetic BDNF agonists to grow new dendritic spines,
Right.
when we modulate actin proteins to rebuild a severed neural connection, we aren't just healing physical meat. We are literally physically rebuilding the universe's biological antenna for consciousness, one single entangled molecule at a time. The next time you think about the grueling process of recovery from a brain injury, consider that it might not just be a biological process. It might be a literal quantum reawakening.
Thank you for joining us on this incredible deep dive. Keep asking questions, keep looking past the classical surface into the deeper mechanics of reality, and we will see you next time.